To wrap up the last little bit of Chapter 5, we will investigate bond energy for a few minutes. First, a definition. What is bond energy? Okay? When two atoms are at some distance from one another, they feel little interaction. As the two atoms get closer and closer, they begin to interact with one another and ultimately form a bond. Those are terrible little circles, but you get the idea. Okay? The process of going from far apart to stably connected releases energy. Perhaps in the form of heat, perhaps in the form of light, kind of depends, but energy is released. So bond energy, by definition, is the energy released in the formation of a bond between atoms, between two atoms. Okay? Here is a table that I have taken out of your book from page 192, showing different kinds of bonds, single bonds, there's some double bonds, there's probably even a triple bond somewhere, maybe not on this page, okay? And each of them have a corresponding bond energy. Notice that these are all shown as positive values, but the energy is released, okay? And if energy is released in the formation of a bond, then the opposite must be true if a bond is broken. If the bond is stronger, even more energy is released when the bond forms. So you can use the magnitude of the bond energy to indicate the strength of a bond between two atoms. So here's something to consider. If you look back in a moment to the previous screen, can you determine whether a CBr or a CCl bond is a stronger bond based upon the bond energies that are given? So pause the video, scroll back a bit, and see if you can answer this question. After checking the values, you can see that 328 kilojoules per mole are released in the formation of the CCl bond, whereas only 276 kilojoules per mole are released in the formation of the CBr bond, and so this is a stronger bond. We will get into more of this when we study bonding in more detail. So the reason this topic comes up in Chapter 5, rather than later in Chapter 9 or 8, when actually it could be there as easily as it is here, but this is an energy concept, and it's actually possible to use these bond energies to estimate enthalpy changes for chemical processes, okay? What we do is we look at the bonds that need to be broken and assume that that energy must be put in to break the bonds. And then we look at the bonds that are formed and say that, well, that energy would be released, and then we look at the net result. So for the reaction down here on the bottom of the page, we would need to break the HH bond and the OO bond. And then these bonds will form between the H and the O. So let's take a look at this and see if we can use the bond energy table to calculate the delta H of this reaction. First thing we have to do is balance the equation. Make sure that we have an equal number of atoms on the left and the right. If we don't balance, none of this is going to work out correctly. Okay. The bond energy table tells us that the bond energy for the hydrogen-hydrogen bond is 436 kilojoules per mole. However, we are breaking 2 moles of those bonds because of the coefficient of 2 here. Okay? And the bond energy for the OO double bond is 495 kilojoules per mole, and that's only happening once, so I can leave that. And I am going to give these positive values because this is the energy being put in to break the existing bonds. The energy of the HO bond comes in at 463 kilojoules per mole. And in fact, what's happening here is, because I have 2 water molecules, I'm actually forming 4 of those bonds. So I'm going to take this energy and make it negative, and then I'm going to add these 2 up. Okay? So get out your calculator, do the math. The total energy required to break the existing bonds is 1367 kilojoules. The energy released from the formation of the bonds in the product is 852 kilojoules, and that's negative. And so the delta H for this process is the sum of these 2 numbers, negative 485 kilojoules per the reaction. And so the formation of water from its elements is an exothermic process. And you know this because the value is negative. Here's one more example for you to take a few minutes to work out using the bond energy tables in your book. The reactants are CH4 and O2. The products are carbon dioxide and water. Be sure that you balance the equation first. So pause the video now, work this problem out, and then you can start her back up and see how you did. First, we balance the equation. We need 2 waters, and we need 2 oxygens. Okay, so you can see here the finished work. We are required to put in 2,642 kilojoules to break the existing bonds. Through the 3,450 kilojoules are released in the formation of the new bonds, and so the net is a release of 808 kilojoules per the reaction as balanced.